Okay, so now let's look at the local versus average mass transfer coefficient. So this is the local mass transfer coefficient that we just derived together. And we know that this local mass transfer coefficient varies from point to point along the surface. And as mentioned previously, the concentration gradient decreases with x, therefore the local mass transfer coefficient would decrease the further down you go across over the plate. So to characterize the overall mass transfer performance of the surface, an average mass transfer coefficient needs to be defined. And so we defined it in a similar way, where we put a dash above the coefficient to infer that this is an average. And essentially, we integrate the local mass transfer coefficient over the entire surface and divide it by the total area. And this gives us the average mass transfer coefficient. In practice, similar with the convective heat transfer coefficient, the mass transfer coefficients and correlations are typically provided for average coefficients, not for local values. So the total then mass transfer rate can be expressed using this equation, where you have the average mass transfer coefficient multiplied by the surface area multiplied by the difference in the concentration from the surface to the bulk. And again, because we're talking about a specific case of a flat plate, then we know that the local mass transfer coefficient only varies with distance x from the leading edge, because the width of the plate is constant. Then in this case, the average mass transfer coefficient can be, this says heat, this is wrong. The average mass transfer coefficient equation can be reduced to this expression. But anyways, you write down this expression because that is the official expression, and then you could solve all the different geometries as you come across them. Okay, so next we're going to talk about boundary layer similarities.